supposed to be able to do that. All right, so chapter 5. So we did nuclear reactions. We've talked about reactions a little bit, but mostly we've kept out of reactions, haven't we? And now we have to start finally covering chemical reactions. My goodness. You guys probably expected that a long time ago, didn't you? All right, so we're going to be talking about a variety of different aspects for chemical reactions. One of the first things we need to talk about is thermodynamics. So nutritional labels, these list the number of calories that the food contains. They're a measure of the energy content of that food. Note the capital C in calories here. That calorie that's on the back of a package, that is actually 1,000 of the lower C calories. Okay? The lower C calories being the actual unit. So understanding how energy and heat are exchanged in chemical reactions actually is the area of chemistry called thermodynamics. It's how we understand the overall expense or output of heat. Okay? You can think of it a bit like balancing our checkbook in terms of energy. So when you eat, food molecules are going to be broken down by your acid and enzymes in your digestive system. The majority of your digestion actually happens not in your stomach, but in your intestines, right? But that's one of the main things you're doing with food, right? You're breaking it down to get energy. So the study of the pace or rate of chemical reactions, this is called reaction kinetics. So you can subdivide all the things that happen around you, okay? You have thermodynamics, will it happen, okay? Is it going to be driven forward on its own, or do you have to force it forward, okay? Then you have kinetics, how fast it happens. So for example, does anybody know what happens if you leave gas in your tank for a couple of years and don't use it? Okay, try not to talk over me a bunch, please. Thank you. So it will evaporate a little bit, but the bigger concern actually is the gas in your tank right now, it's reacting with the atmosphere. And so that gas will react in your tank, and it will actually clog up your tank. Okay, it will no longer become burnable fuel. And what will happen is you'll have to exchange it with new gas. If you try to run that vehicle, it will actually just flood the vehicle, and then you have to clean out the engine. Okay? So, the reason that's happening is gas does what if you put a match to it? If you get it started? Catches fire. So, thermodynamically, it's very favorable for gas to burn, right? It'll burn the whole tank of gas, boom, right? In fact, it'll be quite kinetic in its burning, won't it? May even explode on you. Okay? Now, why is your vehicles not all exploding out there? What is not being provided to all those vehicles with gas in their tanks right now? Yeah, we don't have enough heat to get going, right? And so what we're looking at is thermodynamically, the gas wants to burn. Okay, it's very energetically favorable. Kinetically, it's happening really, really slow right now. Okay? And so what would happen is it is slowly oxidizing in your tank. If you provide it more heat, a bigger push, you're going to make that happen much faster. Okay? And when something happens really, really fast, we call that an explosion. All right. Everybody good with that so far? Okay. So, Chapter 1, we defined energy as the capacity to do work. Chemical reactions involve an exchange of energy between two different substances. You have energy dissipated in some reactions. Energy is transformed from potential energy into kinetic energy, or vice versa in other reactions. You can very familiarly know this because you intake fat, you transform it into energy, you go running, right? And then you sit there and let that energy accumulate, and you produce fat, don't you? Okay, so you're actually doing those reactions in your body. So remember that when you have chemical reactions, the reactants always appear on the left. Those are reactants over there. You then have the yield arrow in between. That's like a directional equal symbol, right? And then you have your products that appears on the right. And that's the notation for reactions. So let's go and talk about heat in a reaction. So reactions that give off heat are called exothermic. Exo meaning out, thermic meaning heat, right? And so exothermic reactions would be things like the gasoline burning, wouldn't it? That's highly exothermic. Okay. This would also be another exothermic reaction. So we have heat as a product is putting heat out. Right, so this right here is then going to be reactions that absorb energy. These are endo meaning within, and thermic, of course, heat. And so endothermic, taking heat in. Now what that means is they take heat away from anything touching them, right? Okay. And so for example, this would be something like a cold pack. If anybody's done a cold pack before. You mix the water and the salts, and it gets cold, right? And so this is a cold pack. Okay. Again, it is pulling heat from the surroundings and incorporating it into the chemical change, or in this case, phase change. Okay. Same thing happens with like ice cubes. If we're making an ice cube, we're pulling heat out of the ice, aren't we? Okay. We're pulling heat away from the water. If we have an ice cube on our hand, the ice cube is pulling heat from your hand into itself, isn't it? So the ice cube melting, endothermic, right? The ice cube freezing, exothermic. Okay, so let's talk a little bit about changes in enthalpy. Enthalpy is a very, very specific measure of heat flowing. So we can think of the exchange of heat energy in a chemical reaction as a more general thermodynamic term. This is going to be called change in enthalpy, or more specifically, just enthalpy. This is delta, meaning change. This is the capital delta. So we have whole changes. Okay? And this right here is the symbol for enthalpy, which is an H, capital H. Okay. So in an exothermic reaction, he is going to leave the system. He's going to leave with the products as we proceed through the reaction. And so our exothermic change in enthalpy is going to be exothermic, which is a negative number because it is leaving the compound. Okay. Endothermic, on the other hand, means energy is being absorbed, and so our energy here is going to be a positive change because we're absorbing energy from the surroundings. We're taking it in. Okay. And so delta H is a positive number. This is actually how you would calculate delta H for a reaction. You have the delta H of the products minus the delta H of the reactants. So, just the difference in the enthalpy, right? Okay, let's talk a bit about randomness. So, we have two factors that are always affecting whether something's going to happen on its own or not. Okay? So, the two factors that affect, is something going to happen on its own, or do you have to try to force it? Is enthalpy, which we talked about before. And so things tend to proceed if you have a negative enthalpy, right? And everybody's probably aware of that. For example, if we start a fire, what ends up happening to the gasoline? It just keeps burning on its own, doesn't it? Okay? What if you try to shove a boulder up a hill? Does it keep happening on its own? Keep going up the hill once you start? No, it does not, does it? Okay, so that's non-spontaneous. It's actually spontaneous in the other direction, right? So if we let go of the boulder, what's going to happen to it? Uh-oh. What happens to a boulder if we let go of it? We're rolling it up the hill, we let go. Goes down the hill, yeah. That means it's spontaneous in the other direction for that reaction, okay? And so the other thing we need to determine and concentrate on is a measure of randomness. Okay? So there's actually a much better way of thinking about this than what your book does. I'm going to give you sort of an entry level to this so that you can kind of understand it at least a bit. Okay? So this is going to be what's called entropy. Okay? Oh, whoops. That's funny, I copied that. Does your book have it labeled correctly? in the introduction to it? Okay. Okay, so this is randomness in a system. This is change in entropy. It's actually spelled right here. Entropy. Okay, and so that is going to be delta S. That's change in entropy. It's going to be, simplest put, a measure of randomness or a measure of options. Okay? Anybody had probability yet? Or taking probability? No? Okay. It actually is heavily tied into probability. What could happen will happen. Okay? All right, so entropy, measure of randomness. Now, changes in entropy are going to be where you have the entropy of your products minus the entropy of your reactants. And this is going to be a measure of the overall randomness of your system. Positive entropy changes are going to be spontaneous and move forward on their own. Negative entropy changes are going to require you to force it. They're going to be spontaneous in the opposite direction. This is actually why, for example, gases expand out. If you drop dye into a liquid, what happens? It spreads out, because these are all increases of randomness, increases of entropy. Okay? Surprising number of your bodily functions are actually driven by entropy changes, not enthalpy changes, if you're ever curious. All right, so we have these two terms that are telling us if something spontaneously goes forward on its own power, right? We have enthalpy, we have entropy. We need to relate these so we can tell if something will spontaneously happen on its own. So this is actually referred to as free energy or Gibbs free energy, which is delta G. So that's Gibbs free energy. If it's a negative delta G, it spontaneously happens on its own. If it's a positive delta G, it spontaneously happens in the opposite direction. Okay? So the previous case of us rolling the boulder up the hill, right? That's non-spontaneous rolling the boulder up the hill, right? It won't happen on its own. We have to expend energy to make it happen. Okay? That would have a positive Gibbs free energy. If we let the boulder go and it starts rolling down the hill, that has a negative Gibbs free energy, right? So it spontaneously happens in that direction. What would a Gibbs free energy of 0 tell you? So if it's negative, it's spontaneous happening. If it's positive, it doesn't happen spontaneously, does it? Okay, so what does 0 mean? It could go either way, right? That this is something that's what's called equilibrium. Okay? It means that both things are probably happening at the same time. Right? Okay, so again, G, Gibbs free energy. Delta G, Gibbs free energy change, or change in Gibbs free energy. This is actually the formula that relates these two things. Delta G equals delta H minus the temperature times delta S. Remember, this is enthalpy, this is entropy, right? Okay. Why does a ice cube melt at 0 degrees Celsius? Why do things become spontaneous when you change temperatures? So we're below 0 degrees Celsius. We spontaneously make it water go to solid, don't we? We go above 0 degrees Celsius, what happens? Water suddenly starts spontaneously going to liquid, doesn't it? This is the formula that tells you that. So if you were to put 0 degrees Celsius here, you'd actually get a 0. Because that's the break point, right? Lower than 0 degrees Celsius here would actually give you a negative number for going to solid. Okay? If we were to go above 0 degrees Celsius, we'd actually get a positive number for it being solid. Right? Meaning it's spontaneous going to liquid. Okay? So this formula is actually determining millions of things around you every second, isn't it? What's liquid? What's solid? What's gas? What's spreading? Everything. Okay? There's actually a kind of an interesting saying that has to do with this formula. So if enthalpy is God's right hand, entropy is his left hand. Because everything that happens around you happens because of these two factors.
What does the T stand for?
This is temperature. So Gibbs free energy tells you if you're spontaneous in one direction or not. This is delta H, enthalpy, temperature, entropy. And notice the negative here is flipping this one sign, because this was spontaneous for being positive. That making sense? Okay. I just taught you something profound. Like everything in your life is happening because of this. Okay. So because the delta G includes contributions from the exchange of heat energy, from randomness, and from temperature, this is actually referred to as gonic. So exergonic is giving off energy for the delta G. Endergonic is requires energy, takes energy to go forward. The exergonic reaction, free energy of the reactants is going to be greater than the free energy of the products. Delta G will be negative. We'll call that exergonic. Does not require you to input any energy. Once it gets started, it's going to go on its own until completion. Okay. That's referred to as a spontaneous process. It's going to occur with once you've started. Doesn't require any energy to be input. Doesn't require any energy from the surroundings. It will in fact release energy into the surroundings. Okay. This is again some examples of thermodynamics. So reactions with a positive delta G do require you to input energy. It would be like going upstream, right, in a canoe. So you continuously have to put in energy. If you stop putting in energy, what happens? You start going backwards because the river pushes you, right? Okay. So that's called a non-spontaneous process. They don't occur naturally. They require you to input energy for them to occur. If we go the other direction, for example, so if we go upstream, we have to continuously input energy, right? If we look at going the opposite direction, that is a spontaneous process, right? Okay. All right, so the Grand Canyon forming, was that a spontaneous or non-spontaneous process? That has to be a spontaneous process, right? Because nobody was sitting there digging it, were they? It's a heck of a digging project, isn't it? Okay. Kinetically, was that a fast process or a slow process? Yeah, it's a very slow process. So keep those divided in your head, please. So again, this is thermodynamics put into charts. So again, this would be the G of the reactants, G of products, and what we can see here is that we would end up with a negative delta G, right? And so that is a spontaneous process. Right here we have an endergonic reaction where our G of products is larger than our G of reactants, and so that would give us a positive delta G, or a non-spontaneous process. So a living system's free energy is going to be the energy that can do work under cellular conditions. During a spontaneous change, the free energy decreases and the stability of the system will then increase. In a living system, the free energy given off in one chemical reaction is going to be coupled as input to another chemical reaction, and so we always end up with reaction pathways. Okay? And typically they end up in cycles, because you always have to couple reactions with another reaction. Anybody ever heard of ATP? Okay. That's actually an energy carrier. What you oftentimes will do in any reaction is you'll actually use phosphates from the ATP. You'll couple that reaction of losing phosphates to another reaction your body wants to perform. Okay. It'll put a phosphate on something. That'll make it high energy and spontaneously go to something else. Okay. Kind of like you can set up like a trap, right? Or dominoes. To one after another, click themselves down. Okay. Very common method for your body to use. So again, that main molecule that's going to transport energy is referred to as ATP. It's a temporary energy storage. It actually breaks down. It spontaneously breaks down over time in your body. Did you guys know that? Yep. It takes approximately 2 days. Yeah. So you'll start losing significant amount of ATP if you don't make any more in about 2 days. Yeah. On the third day, you'll have lost most of it. And so ATP is not actually stable. It'll spontaneously break down in your body. So spontaneous, you eat food, you undergo spontaneous exergonic reactions that will generate ATP. You will then have non-spontaneous endergonic reactions, such as using the ATP to walk, breathe, think, do this class, do homework. Right. So let's talk about kinetics now, okay? So when we were talking before, we were really talking about like a stairway, when we get in from the top to the bottom, right? And so, for example, if you go from the top of the stairs down to the bottom stairs, well, once you get started, you don't actually need any more energy going in, do you? If you stop providing any energy, you're still getting to the bottom of the stairs, aren't you? Might hurt, but you're getting there. Okay? The opposite way, which is the endergonic, right? That's going up the stairs. That requires continuous energy input, right? What if I just stop providing any energy input when I'm at the top of the stairs? What happens? I fall back down, don't I? Okay? Yeah. And I'm going to hurt, and I'm going to end up back at the bottom, aren't I? Okay. Okay, but what you notice here is that it takes a certain amount of energy to go from one direction to another and to overcome that barrier between them, right? So, for example, when I'm sitting at the top of those stairs, if nobody touches me, I'll actually be balanced for a while, won't I? And you often see rocks on top of hills like this, right? Where they're actually balanced there. Nobody shoved them, so they just stay, right? Okay, and this is referred to as that little push that needs to be done. Specifically, it's the activation energy. It's the energy you need to provide to get things started. We started all of this with burning the gasoline in our car, right? Okay, what's the activation energy for that? What do you need to get that started spontaneously? To really go? The match or the spark, right? And so that match or spark is actually the activation energy. That would be this process right here. So we have the gasoline here. We provide the first input energy that gives the energy to overcome this barrier here, called the activation energy. Okay? We would then go to products, which would then release more energy. That extra energy is going to provide the activation energy for more molecules to this process, and we get a chain reaction where everything burns, right? Okay. And so that's just recycling this energy back in, overcoming the activation energy, and we go faster and faster and faster as we provide more energy available. Okay? This right here, this activation energy, that tells you the speed of something happening. Right? If you can overcome this barrier really fast, the reaction will go very fast. If you can't overcome this barrier very fast and you don't have enough energy to jump over that barrier, you're going to be a very slow reaction. Okay? Think of this as the Disneyland turnstiles, if that helps. Okay? Or does anybody still walk to things? Sometimes? Okay. This would be like the hill between you and the school, right? If it's a small hill, you can go real fast to the school, right? If it's Mount Everest here, it's going to take a while to get to school, isn't it? Okay. Okay. So again, that's the kinetics. This right here, this activation energy, is actually the energy that you need to begin the reaction. It's going to be used for things like collisions being meaningful collisions. Okay? It's going to be used for things like them being able to collide often. Right? So, by the way, what happens if you increase the temperature in your oven? What happens to cooking? Happens faster. Yeah. This is actually what you're doing right there. So you provide the temperature to cook, And that is, right there, a typically non-spontaneous process. Okay? So it'd be like this. And if you increase the temperature, you're going to get over this reaction barrier easier, faster. And so you make the reaction happen faster. Typically, it's something like every 40 degrees Fahrenheit, doubles the speed. Okay, so this is the energy content in food. Whenever we're talking about using energy for our bodies, we're typically talking about burning calories. Burning's a pretty good analogy for this. So outside the body or inside the body, when your action reacts with a molecule, oxygen reacts with a molecule, we're going to produce carbon dioxide, water, and energy. That's called combustion when we do that outside the body. We undergo a very different pathway for this, but we actually get the same sort of products. We get oxygen, water, and carbon dioxide. Okay? So we use oxygen, get carbon dioxide and water, and energy out of the process. And so we refer to it as burning. We are not literally doing combustion in our bodies. Okay? Whenever we look at the food that we have, we look at the back of the energy, the labels, and what we'll see is we have this labeled like this so, right? And so we have the grams of carbohydrates. For every gram of carbohydrates, that's going to give you 4 capital C calories. That's actually a kilo lower C calorie, okay, which is the actual unit for calories. Remember that gram of water heats 1 degree Celsius? Yeah, for this amount of energy. That's lower C calorie, okay? So proteins also are going to give you approximately 4 calories per gram of the protein. Fat is going to give you 9 calories per gram of the protein, of the fat, excuse me. You'll notice that these are higher energy, so you can actually have them much more condensed energy. If anybody wonders, this is actually why humans make fat and store our energy as fat, is so we can weigh less and have more energy. Plants, on the other hand, tend to store it in carbohydrates because they don't care how much they weigh, do they? Yeah. Weighing more is actually not necessarily a bad thing to a plant. Okay. This right here is actually the energy in kilojoules, and you'll see that on all the packages as well. They actually have to list them both ways. Okay. So this would be your thermodynamics for your food right here. Here we have some common food items broken down into their carbohydrates, protein, fats, and their calorie counts, which would just be these numbers. This times 4, times 4, times 9, added together, right? Everybody good with that? Okay, fantastic. So this right here is your, again, fat count, carb count, protein count right there. And then we times 9, times 4 here, times 4, and we get our calories over there. If we want to know our total calories, we add all those together, right? And again, remember that these will be capital C calories, so capital C AL, right? Okay, so let's talk a bit about low-calorie foods. Most of the calories in soft drinks actually come from sugars. This is why they're a real problem for our current society, really messing with our health, right? Okay. We're getting way too much sugar now. It's causing just havoc on every aspect of human health in the U.S. So sweeteners that do not have sugar undergo very few chemical reactions in the body, and they do not produce much energy. So what we do is we give something that your taste buds say, hey, this is sugar. And then your body can't actually break down and use as carbohydrates. Okay? This does mean that's going to come out as waste. Do you know what the stuff you don't digest comes out as waste? Okay, the stuff you do digest comes out in your urine. The stuff that does not get digested comes out the other end. Okay? And so that's fecal matter, right? Okay. And so does anybody know what like Splenda and all those different sugar substitutes, their leading side effect is? No? Really? Anal leakage. Because they concentrate the the stuff that's coming out of you, if you eat a lot of it, in such a way that they'll actually cause it very difficult to actually hold your bladder. So, kind of a fun thing. Little fact there, right? Okay, so again, your fats are going to produce the highest amounts of energy per gram when they undergo chemical reactions in your body. Manufacturers of baked goods have actually introduced fat substitutes. This has produced low-fat alternatives. Dextrin, cellulose, and gums are going to be carbohydrate-based molecules that produce less energy when eaten. They've become a more popular thing than just artificial sweeteners. Because they tend to cause less overall problems. Okay? Anyways, I will stop here. You all have a wonderful day. And I will see you all Thursday. We'll talk more about energy. So you guys can be energetic.